Okay, physical science time. Welcome to physical science time. You are very welcome here. In the world of science today, which is just the world, in the world of science today we're talking about acoustics. Acoustics. I'm going to ask you a question that I'm worried you won't be able to answer. But do you know how do you know the word escuchar in Spanish? Because that's related to this. You don't. Does any of you speak any Spanish at all? Okay, well that's a dud then. I'm trying to think of another thing in English maybe. Do you know the word escuchar? It's the verb to listen or to hear, kind of like to hear. I think, and many people, the comments are enabled for this video, could probably correct me if I'm wrong, but I think it's generally used in the way of to listen as in like to not only hear information, but to actually understand. And so this comes from, my point is, it would have worked better if you had known the answer, but it comes from the Latinate, the Latin word for to hear. So we're talking about sound, basically. We're talking about the study of sound. It's called acoustics. The objective that we're trying to meet is plan and carry out investigations of acoustics. So please write that down. I mean, I guess you have it in your lab. Plan and carry out, and really this objective applies more to a lab. Plan and carry out investigations of acoustics. And so really, I guess in a sense, you've already met that objective by planning an investigation of acoustics and carrying it out. But now we're going to discuss, as we often do, your findings. So let's start with that then. What did you learn about sound from your lab? Did you learn anything about sound from your lab? I hope the answer is yes. Okay, good. That was a yes and no question. Now, explain to me what you learned about sound from your lab.
We learned about how there's different notes.
Okay. So actually, that's a great thing to start with. So the frequency of remember we talked in the last discussion about what frequency is in general with waves. Do you remember that? So frequency, would you remind me? Would you redefine for me? Reiterate the definition of what is frequency in general for waves? Someone else. You talk too much. No, I appreciate you involving yourself in the discussion. But I wish I could appreciate more this crew involving themselves in the discussion. So would someone please at this table remind me of what frequency means in general?
How fast the wave?
Yeah, that's the speed. Really, wave speed is how fast, but I know what you're getting at, and it is how many waves pass in a certain amount of time. How many waves pass? Remember, the unit for frequency is, and it is in sound waves just as it was in any kind of wave, hertz, or inverse seconds, which we also sometimes write as 1/seconds. And so frequency is how many waves pass in a given amount of time, usually a second. And so you can kind of see with 1/second here, it's really waves over second. It ends up being how many waves over a second, but a wave is not a unit, and so the unit is just 1/second. And so if we had a wave that had a frequency of 440 hertz, that means that what? Yeah, 440 waves pass by a certain point in a given amount of time, which is 1 second. And that happens to be, this is what we're getting at here, that in sound, frequency is what? What do we hear, since it's sound, what do we hear frequency as? Yeah, pitch. Pitch. So greater frequency in sound, greater frequency equals higher what we would call pitch in music. So the faster the wave is moving, the higher the tone we hear. Can you give me an example of a low tone or a low pitch? Okay. I mean, could you produce with your own little sound producing organs low frequency? Yeah. Now could you produce a high frequency? or even if I can do it. I'm not a good whistler, but in general, actually, this is a little side note, but for a given human being, I think there are some exceptions, but for most people, the lowest tone you can produce, I forget its actual name, I think it might be called a glottal something, but it's a sound that, if you've ever seen the movie The Grudge, which is not a sponsor of this video, and other horror movies are available, but the sound that the chick in The Grudge makes when she's trying to haunt people, that thing, you can, if you get lower, that's the lowest sound your body can usually make, or I should say your vocal organs can usually make. And the highest pitch that you can make with your vocal organs is whistle. I'm not a good whistler. Me and Peppa Pig are not good whistlers. If you don't get my reference, look at YouTube and search in Peppa Pig whistling, because it is one of the funniest parts of Peppa Pig, in my opinion. Anyway, so the higher the pitch, the higher the frequency, the higher the pitch. And so if we, I think, I might need correction if I'm wrong about this too, but I think pianos are usually tuned to, for example, 440 hertz, which is an A on the piano. And so the kind of the middle A on a piano, that almost certainly is not what it actually sounds like. I do not have perfect pitch, but the middle frequency A on the piano is what a piano is tuned to usually, and that has a frequency of 440 hertz, which means that if I hit that key on the piano or the violin or the saxophone or whatever, that 440 vibrations are interacting with my ear every second. Kind of a lot. And so we measure sound with frequency as the pitch of sound. What other qualities does sound have? Let me change colors here, actually. Yeah, good. Thank you. And I'm glad you said that one next, because we didn't really talk about this one a whole. In fact, I don't know that we talked about it at all in the wave video, but it was in your book. Sound, and what part of the wave, or what principle about waves relates to volume and sound? Do you know? No? No? The other one. We did diagram it, but we didn't discuss what it means. Yes, but there's a different name for that, and yes, exactly right. Amplitude, and you'll recognize the word amplitude. This also relates to, if you've ever heard of a guitar amp, not the same thing as amperes that we learned about when we were talking about electricity, but it relates to amplify. Amplify means to make greater. So amplitude is the greatness, the height of the wave. So I'm going to put that in here. This is measured in what? Do you remember? If we're measuring the height of a wave, that's not exactly the same thing. I shouldn't say that, because height of a wave is actually the distance from crest to trough. If you remember, let me just diagram a wave real quick here. Wave height is actually this distance, and amplitude is this distance. So we're talking about this one. It could also be this one. It doesn't matter whether it's crest or trough, but it's the distance from the baseline to the highest point or the lowest point. And so what will we measure that in? Probably in, yeah, some variation of meters. Maybe it'll be nanometers or millimeters, but some variation of meters in the SI at least. And as we said before, for sound, what quality of sound does that manifest as? You already said it. Sound what? The greater the amplitude, the greater the what of the sound. Yeah, what we call sound volume. And at this point in the year, I like to specify sound volume, because we already at the beginning of the year, remember, we learned about physical volume, like how much pink drink is in my cup here is a physical volume, right? And that's different from sound volume, but they both come from the same kind of idea, that how much it fills up. So if my cup is half full because of a certain volume, that relates to, maybe we might think of sound played at a medium volume fills up the room a little bit, but if I increase the sound volume, it fills up the room even more. That's one way to remember it. So sound volume, and we measure sound volume in decibels. Decibels are the measure for sound volume. And interestingly, the scale of decibels is a logarithmic scale, and so every incremental increase on the decibel scale is actually 10 times louder. The book says, on this scale, the faintest sound that most people can hear is 0 decibels. Sounds with intensity levels above 120 decibels may cause pain and permanent hearing loss. And so there's actually a kind of neat little, you can look these up online. I was going to show it, but it might not be very worth it. But there's on page 329 in your text, or you can look them up if you go to www.yahoo.com and type in decibel chart. I'm sure you can find the varying amount of sound volume that certain common sounds have. For instance, the book says that just the ambient noise in an average home is 50 decibels, where a jet plane taking off right next to you or a certain distance away would be 150 decibels. When I mowed the lawn the other week, this tells me that the decibel level was about 110, which is just short of the hearing loss threshold. And I was playing music in my ears louder so I wouldn't have to listen to the lawnmower. I said, what does that say about me probably hearing loss? That's probably why I thought Joe was mumbling. He wasn't. I just can't hear anything. But it's okay, because all I have to do is talk. My job is not to hear, it's just to talk. Okay, so what other things do we have about the properties of a sound wave? That's a great point. We should really put that up here. All sound is vibration. Every sound that has ever been made is a vibration of matter. We talked in the last discussion about how energy is what flows through a wave. Remember, we said matter doesn't actually move from place to place in a wave. It's the energy that is moving. Do you remember this? And that's true of a sound wave too, but a sound wave does require matter. Sound only travels through matter. Actually, one way to think about sound is that it is the vibration of matter. When I'm speaking, as I almost always am, it's not the air from my lungs blowing across the room and getting in your ears and carrying the sound, right? It's that my vocal cords and mouth vibrate in a certain way, and the air itself vibrates in that same way, and then eventually gets to your ears, and when I say eventually, like instantly gets to your ears, and causes your eardrum to vibrate, and then that's what your brain registers as sound. And so all sound is vibration, and it's always in matter. It always has a medium. In space, no one can hear you scream. You might have heard that, because I don't know where that comes from, but I would guess some other horror movie. This video is not sponsored by horror movies, but in space, when it says that, it means that there's no matter in space, and therefore there cannot be sound in space, because sound requires a medium that can only move through matter. It's always a vibration of matter. And by the way, what kind of wave would we say sound is? You might remember this from you got it, sound wave. That's exactly what I was looking for. No, come on. Well, of the two main kinds of wave, other one. Compressional, yeah. So I don't think we actually mentioned this in the last video, and I'm going to switch colors from green because I don't think it's going to be very visible. Pink, that'll probably work. There are two main kinds of waves in nature. We diagram transverse waves, where the energy flow is in this direction, for instance. It could be the other way, but the energy is moving this way, and the wave oscillation, the movement of the wave itself, is perpendicular to that. It could also be perpendicular this way. That the same wave could move out in space, as it were out of the whiteboard. Of course, I can't diagram that. But it could be either way perpendicular. Whereas in a longitudinal, or sometimes called compressional wave, if the energy is flowing in that same way, the wave matter, or the wave motion, is in the same direction. We usually indicate that as areas of compressed air, perhaps, compressed water. It doesn't matter as long as it's matter, but compressed matter, called a compression. Alternated with, I might say rarefied, but spread out matter, which another word for that is rarefied, called a rarefaction. A way to remember this word is that this, like I just said, these areas where the matter is more spread out, rarefied means kind of like it has been made rare, right? Like there's less of it here. You know what rare means? Not like rare like a steak, but rare like diamonds, which aren't really. But the matter has been made more rare. There's less of it for a given volume of space here than there is here. So compressions is where the matter is compressed, and rarefactions or rarefications, just depending on who is saying it, are where the matter is more spread out. So that's really what a sound wave is. This one is a sound wave. If I clap, what's happening is I'm compressing air here, and then that compressed air, the air itself does not move, remember, but it bumps into other air, which bumps into other air, which bumps into other air, and we get a chain reaction of compressions all the way to your eardrums, and you hear the clap. Like when you're on Facebook and someone puts the clap emoji. How rude. So there's a compression, and then the reason a rarefaction happens is because that air had to come from somewhere, right? Like the air that was compressed, I'm not scooping up, but it's kind of like I'm forcing air that was this whole area, and what? Do a loud clap. Yeah. Wow, that's a really loud clap. Because he's really compressing the air. And loud clappers will know that you need the little, pocket. You get a little pocket in there, and that's where the air is getting super compressed. You're getting a little black hole of air. That's not true. That's not true. Although there is interesting research in analogs of black holes, what we say as regular, space black holes that are so fast that light can't pass through them, to what are called acoustic black holes, where it's where the air is so compressed that, I shouldn't say that, but where sound waves can't escape, and they use those as analogs. Anyway, so we have compressions and rarefactions in a sound wave, and then when the sound is produced, remember all sound is made by vibrations, but also every vibration produces sound. Sometimes the sound is very, very small. It has a low amplitude. And by the way, where amplitude we might diagram on a transverse wave as that, and this is also, we do use these to diagram sound waves, the amplification or the amplitude of a sound wave is how compressed the compressions are. So you might remember that Mason's clap there was louder than mine. I'm going to do a little clap, and Mason's going to do a big clap. And the reason his is big, his sound volume is big, is because the compression is more compressed. And so the bigger the difference between the compressions and rarefactions. What would be the limit of this? If all of the matter was in this compression and there was nothing, there was a vacuum between the rarefactions, you know what that is? Make a little guess. It would be the loudest sound, right? It would be the loudest physically possible sound. There was no matter in the rarefactions. All of it was into the compressions. You can even, sometimes it's so strong you can see it on a video. What would the loudest sound be? Can you think? Louder than that even. You might have even read an article or something about, or I shouldn't say read an article. That's ridiculous. You've watched a TikTok or a YouTube short about the loudest sound maybe ever from Real Life Lore, at Real Life Lore. I don't actually know if they have this video, but I assume they do. It would be an explosion. That's what an explosion is. That's one way to think about an explosion. Even something like a firecracker. One way to think about an explosion is that the air gets so compressed that it draws all the air out from in between them, and that's called a shock wave. And if you've ever seen, and if you haven't, you should probably, I think they're cool to look at, but if you've ever seen military ordnance being discharged in a YouTube video, you can see the shock wave. Like the grass on the ground will move in this way, that it'll all compress together, and you can see the shock wave moving as you watch the explosion transfer. So that would be, another example of this is a sonic boom. This is exactly what a sonic boom is. An aircraft moving faster than the speed of sound produces a sonic boom because that object has compressed air so much in front of it that it's now, even the air is visible. It's actually water vapor in the air that's visible, but it's causing this extremely loud sound, which in that case is called a sonic boom, but it's a type of shock wave.
I think the loudest sound ever recorded on Earth was in the later 1800s, early 1900s. It was a volcano.
Krakatoa.
Yeah.
That's what I thought you might have seen on. I don't think you watch enough TikTok, or maybe not the right kind of TikTok if you haven't seen some video about Krakatoa. But yeah, I think you're right. That's kind of what I was getting at, is that and why would that be the loudest sound? Well, because it has the most compression. That's what amplitude is loudness. And in sound waves, it is how compressed the compressions are compared to how rarefied the rarefactions are. And so all of the air that was here, air, whatever it is, water, all of the matter that was here gets compressed, gets put into a compression, and that's called a shock wave. Your book has a whole section on music and how music is produced. You will recognize pitch, of course, from music, which relates to the frequency. You'll recognize loudness from music. Other properties of music are things like beat, timbre, or tone. Oh, you're right, Stu. I should have put this in picture 20 minutes ago. And those, I would say mostly, if you know those vocab words, which you should know from what? How should you know those? From doing your vocab, yeah. From the book. I think you'll probably be fine with that. Oh, the other thing that is discussed kind of at length in your book is how your body registers sound. So you have your sound producing organs, enumerate them. What organs in your body produce sound? I guess really technically all of them because they vibrate. But the ones that you deliberately produce sound with are your vocal cords, ideally. Or I shouldn't say ideally. What is the word I'm looking for? Primarily. There are others, right? If you, like your lips, teeth, tongue, little dingly guy, you know what his name is? Uvula, yep. Other aspects of your throat, your lungs. I think you'll find that people without lungs cannot speak. So there's a whole system of sound producing organs. What is your sound receiving organ? The ear. In the past, I have diagrammed this on the board, but I have one right here. I don't even need to diagram it. But what's the purpose of this guy, the outer ear? Yeah, it's like a funnel. It focuses the sound into the hole. And what's inside that hole? Nope, not in me. I run a very tight ship, and so I cleaned this earwax out. But inside the hole is the eardrum, and that is the thing that vibrates in response to sound, which produces, actually what it does is it transfers those vibrations to the smallest little bones in your body. The stirrup, hammer. What's the other one? Malleus is the Latin word for hammer. So malleus or hammer, stirrup or stapes, and
I know it.
Anvil. It's the anvil.
Yes.
And I don't know the Latin word for anvil. I think it might just be anvil. So those three little bones jiggle together, basically. There's a little more complicated than that, but they jiggle together in your inner ear, or your middle ear, and then that transfers sound to a fluid-filled swirly called a cochlea, which is the Latin word for shell. Looks like a little Gary's seashell from SpongeBob. You know about SpongeBob. And then that's full of hairs, and those hairs vibrate in response to the sound, which triggers nerve signals that go to your brain if you have one, and then that is translated as sound. That's what your body, your mind, your psyche records as sound. So it's all about vibration passing along, just in the same way that vibration is passing along in the air from not the air itself from my mouth to yours, well, probably a little, but that's not the point, but the vibration of the air is transferred along through the air, which eventually gets to your ear and the other associated structures.
Isn't that like Beethoven have the metal pipe
Yes.
in the mouth?
Beethoven had syphilis from the time he was born, so he eventually lost hearing. And so I actually saw this, almost all my information, like you nowadays, comes from either TikTok or YouTube Shorts. But I saw, because you've seen, or I had been aware when I was a child that he may have used like an ear horn when his, to better focus the sound. And that would only work if you had even a little bit of hearing. But then when he lost his hearing entirely, when he became totally deaf, he would hold a metal rod in his teeth so that he could feel the vibrations, because sound is vibrations. And so then he was kind of, in a way, transferring the responsibility of registering sound vibrations from his ears to his teeth. Works, I guess, probably. I mean, worked for him, obviously. Made good music, speaking of music. Do you have other questions besides the Beethoven thing? Not about syphilis, probably, but do you have questions about anything regarding sound as a physical constant quality?
If you scream in space, sometimes you hear yourself, or not?
Great question. I like that one. What do you think, guys?
No, probably nothing comes out.
No, yeah, nothing comes out, but I think you would definitely hear your own. Well, I mean, there would be other problems like you suffocating. But I think you would, because of the vibrations, like you don't need, you are matter, right? You matter, that's true, but you are also made of matter. And so there's no matter around you to transfer the sound, but the matter could transfer from your vocal cords up the matter that is you into your ears. Absolutely. I would say almost certainly you could hear yourself scream. So really, that's, in space, no one can hear you scream, except yourself, which is almost sadder and scarier than no one being able to hear you scream.